Modern life depends on one invisible system more than almost anything else: electricity. When that system stops, even for a few hours, the effects begin immediately. Lights go out. Traffic signals stop working. Refrigerators shut down. Internet connections disappear. Elevators stop between floors. What many people don't realize is that a large power grid failure is not just a simple blackout. It can trigger a chain reaction that affects transportation, communication, water supply, and even food distribution. To understand why this happens, we need to look at how the electrical grid actually works. Most countries rely on a highly interconnected network of power plants, transmission lines, substations, and distribution systems. Electricity is generated at large facilities such as hydroelectric dams, natural gas plants, nuclear stations, and wind farms. From there, high-voltage transmission lines carry power across long distances to substations. Those substations reduce the voltage and distribute electricity through smaller lines that eventually reach homes and businesses. Under normal conditions, this system is carefully balanced. Electricity supply and demand must match almost perfectly every second. If demand suddenly rises, power plants must increase output. If demand falls, generation must decrease. This balance is constantly managed by grid operators and automated control systems, but when something disrupts that balance, problems can spread very quickly. One common cause of large outages is damage to transmission lines. Severe storms, wildfires, equipment failures, or accidents can take critical lines offline. If one major transmission route fails, the remaining lines must carry more electricity to compensate. Sometimes they can handle the extra load, other times they cannot. When transmission lines become overloaded, protective systems automatically shut them down to prevent damage. This is an important safety feature, but it can also shift the burden to other parts of the network. If those sections also become overloaded, they may shut down as well. This is how a cascading failure can begin. A cascading failure occurs when one small disruption spreads through the grid, forcing more and more components to disconnect. Within seconds or minutes, a large region can lose power. History has shown how quickly this can happen. Large-scale blackouts have occurred in many countries, sometimes affecting tens of millions of people at once. In many cases, the original trigger was relatively small, such as a single equipment failure combined with unusual demand conditions. Another challenge during major outages is something called grid stability. Electrical grids operate at a very precise frequency. In North America, that frequency is typically 60 Hz. In many other parts of the world, it is 50 Hz. If too much power is lost suddenly, the frequency can begin to drop. If power supply suddenly exceeds demand, the frequency can rise. Even small changes can cause sensitive equipment to shut down automatically. Power plants themselves are also connected to these frequency conditions. If the frequency moves outside safe limits, generators may disconnect to protect themselves. This can accelerate the outage. Another issue appears after the grid goes down. Restarting it, bringing a large electrical grid back online, is not as simple as flipping a switch. Most power plants require electricity from the grid itself to begin operating. Pumps, control systems, cooling systems, and monitoring equipment all need power. If the grid is already down, that power is not available. To solve this problem, certain facilities are designed with something called black start capability. A black start power plant can start without relying on external electricity. These plants may use diesel generators, batteries, or small auxiliary turbines to begin the startup process. Once one plant is running, it can slowly begin supplying power to nearby substations. That power is then used to start additional plants. Gradually, the grid is rebuilt piece by piece. This process can take hours or even days depending on the scale of the outage. Meanwhile, other infrastructure begins to feel the effects. Water treatment facilities rely on electricity to pump and purify water. Without power, water pressure can drop. Fuel stations require electricity for pumps and payment systems. Communication networks depend on power for cell towers, servers, and data centers. Many of these systems have backup generators or battery reserves, but those backups are designed for limited periods of time. If a major outage continues long enough, multiple systems can begin failing together. This is why resilience and redundancy are important parts of modern grid design. Utilities invest heavily in backup systems, monitoring technology, and automated protection equipment, but no infrastructure system is completely immune to failure. Understanding how the grid works helps explain why smaller, localized energy systems have gained attention in recent years. Some households and businesses explore backup generators, battery storage systems, or solar installations that can operate independently for short periods. These systems are not intended to replace the grid entirely. Instead, they provide limited power for essential devices during outages. Even small amounts of electricity can be useful when the main grid is unavailable. Lighting, communication devices, medical equipment, and refrigeration can all benefit from backup power sources. This is why learning how electricity is generated and stored at smaller scales has become more relevant. Many people begin exploring basic generator systems, energy storage methods, and alternative ways to produce electricity locally. Understanding these principles does not mean abandoning the grid. The modern electrical grid remains one of the most complex and reliable systems ever built, but learning how energy flows through smaller systems can provide a clearer picture of how electricity works overall, and in situations where power interruptions occur, that knowledge can make a difference. The key insight is that electricity is part of an interconnected system. Power plants, transmission lines, substations, and local infrastructure all depend on each other. When one piece fails, the effects can spread quickly across the network, but the same principles that operate in large power systems also apply to smaller energy setups. Motion can generate electricity. Batteries can store energy. Circuits can distribute it. Once people understand those fundamentals, energy systems become less mysterious. If you enjoy learning how real-world infrastructure works and how electricity is generated, managed, and sometimes interrupted, consider subscribing to the channel. New videos explore practical engineering topics and explain complex systems in clear language. You can also check the description for a helpful resource that outlines the basic structure of small energy systems and generator setups for people interested in studying how electricity can be produced on a smaller scale.